All right, so let me just our our speaker for today. His name is Noam Soker. He got his PhD in '86 from the in Israel under the supervision of Mario Livio. He did a first postdoc at the University of Virginia from '86 to '89, and then another postdoc at the Center for Astrophysics at the Harvard Smithsonian from '89 to '92, after which he became faculty member at the University of Haifa from '92 to 2003. And since then, he's been a professor at the Technion Institute in Israel. He's well known for his obsession with angular momentum conservation and the role of jets in stellar evolution. And in many cases, his proposed scenarios are far from consensus, like the Gearing jet mechanism for core collapse supernovae. So we welcome you. We are really happy you accepted our invitation. Thank you very much, Noam. The floor is yours.
Okay, thank you. I'm very happy you invited me, actually, because I think this crazy situation gives us opportunities we did not think about. That I'm at home here in Israel and I'm giving a talk to people in Mexico, and I think it's beautiful, and I think we will benefit from this situation in the future as well. I prefer this talk to be informal, so if you have a question, please ask me. Don't use the chat, it's hard to follow. Just open your mic and just ask me a question. It will be better if we put it like this. Okay, so you read my first slide. You see most name in Hebrew actually have some meaning, so it's not unique to me. And okay, I hope you hear me from time to time, please. I see now only windows, so I hope you are there. Okay, let's start. So first of all, I would like to put this talk into a broad view. And this is a little bit of a history. For about 100 years, the main question regarding stars was their energy source. About 170 years ago, in the middle of the 19th century, people talked only about gravitational energy. Some talked about meteorites that hit the sun, but this doesn't have enough energy. So for about 50 people, the idea was that the sun is slowly contracting on a Kelvin time, Kelvin-Helmholtz time, and this can give energy, but for only 30 million years, which is not enough for life and geology. And this is a history, I will not get into it, the big argument between Darwin and his followers and Lord Kelvin. Eventually, it became clear that we need radioactivity and nuclear processes. And in 1915, people start thinking about hydrogen that is turning to helium. And then in 1919, somebody said light atoms such as hydrogen, nebullium, or helium, formation of heavy atoms. Of course, there is no element like nebullium. At that time, they saw spectral line in planetary nebulae. And in these planetary nebulae, they could not recognize these spectral lines. So they say, well, this is a new element. They call it nebullium for the planetary nebula, nebullium. But several years later, it turns out that this is a forbidden transition in the atom or ion of oxygen. So it's not a new element. It was a line at 5,007 angstrom, line of oxygen. And very interesting history, but this is, we're going back to our energy question. What powers stars? And then Eddington said, we can get rid of the obsession that there is no other conceivable supply beside contraction. I told you, Lord Kelvin thought that the sun contracts and this is a supply of energy. And this comment by Eddington, we can get rid of the obsession, is one giant in astronomy says something about another giant in physics, about Lord Kelvin. Now we jump forward after the quantum mechanics, which was invented in the 20s, 100 years ago. and we go to the PP chain, the power stars and CNO cycle. So only about 70, 80 years after people start thinking seriously about powering stars, they actually understood what is going on. Then several years later, Envy Salpeter worked out the triple alpha where helium is burning to carbon. And in 57, there is a classic paper on all sorts of nuclear reaction by these four people. So these were actually this is a century, 100 years or even more, looking for the energy source of stars. So what is my talk about? My talk is part of the, I would say, group of open questions that are related to angular momentum in stellar evolution. And many, many questions are related to angular momentum. And this is how I see it. I see that actually I deal with binary stars, with jets, with mass transfer. These are all questions that are related somehow to angular momentum, directly or indirectly. Now, an evolved star, the star that was on the main sequence, and it expanded to become a giant. Later, it can turn to a white dwarf, which is smaller, but on the way it becomes very large. And because of angular momentum conservations, it will spin very, very slowly. So in evolved star, like red giant, super red giant, asymptotic giant branch stars, and so on, axisymmetrical mass loss, formation of jet, magnetic activity, everything needs angular momentum. And this angular momentum must come from a companion. And this is the relation between binary interaction and jets and accretion disk and non-spherical mass loss. Okay? In some cases, even massive planets can supply the angular momentum, okay, to evolve sun-like stars. And this is something that we're still working on because there are many open questions. So a very short summary of my talk will be jets. I will concentrate on jets in this talk, but as you see, it is related to other things besides jets. So I give you now my full summary and explaining, and then go to some nice picture, and I will end with the same summary that I present here. So if you got the summary here, everything is fine, okay? So I put it kind of, or like you cook something, that tell you how much sugar to put and everything. Here I put people who simulate the following cases must include jets. So I claim that jets related to angular momentum and mass transfer and so on must be included in simulation and in general in the study of explosion of core collapse supernova. These are massive stars where the core collapses to a neutron star or a black hole. And I claim that in many cases, the explosions are driven by jets and not only by neutrinos. Neutrinos do play a role, but jet must be important there. Okay, in this case, it can be a single star because we take a core of 3,000 kilometers, which is collapsing to 30 kilometers at the beginning and then only 12 kilometers. So it spins up and it collapses and there are perturbations and so on. So maybe single star can even give you stochastic accretion disk, which launches jets. Along the talk, I assume that in order to have jets, you need an accretion disk. You have a compact object which accretes mass in a disk, and this disk launches the jets, okay? So in other cases, we need binary companions. So let's move on. Circumstellar matter of some type 1a supernovae. We'll get to it later. Type 1a supernovae are those white dwarfs that somehow explode. In the white dwarf explosion, nothing is left because the carbon and oxygen are burning to mainly nickel, and everything is exploded by the release of nuclear energy. Common envelope evolution, and there are people here who I will show some of the results who also conduct these simulations. In the common envelope, you have a giant. This is a classical. A star expanded to a giant size and swallow another star that spirals inside the envelope. So you have one envelope, two stars. One is the giant itself and its core, and another one is a compact star. The shaping of bipolar planetary nebulae, I will show you many pictures. The formation of equatorial rings. Just an example, because the pictures are nice, I will show you. This is with Muhammad Akashi, a collaborator. Supernova impostor, like Eta Carina, which I show picture of, and another one, it's not important now. A lot, these are intermediate luminosity optical transient, like VH38 Now I'll show you a picture of VH38. This is a picture of VH38 that you see behind me. This is a light echo. The star erupted inside. What you see around are the reflection of light, okay? And all these cases, I claim jets are very important, okay? So what is the motivation? Now, I show you here a picture of cluster of galaxies. This is not star. The size here is about 1 million light years. What you see here is a galaxy cluster, namely, this is a huge cluster of galaxies, and here we see the central galaxy. But what do we see here? We see an X-ray picture. This X-ray doesn't show you the galaxies with the optical light of stars. This picture shows you the hot gas. Hot gas, I mean 50 million degrees. And what do you see in the hot gas? Look on the left. You see holes. And if you look on the right side, in blue, what you see is the radio image. The radio image is actually the image of jets in active galactic nuclei. These are the supermassive black hole that sit at the center of galaxies. So in this, what we see here is a cluster of galaxies, which you don't see because it's no picture in optical. I'll show you in a moment. And we see hot gas. If I give you the entire picture, this is the same as this one, but now a different picture. What you see here, look on the right side. Upper right is what I showed you before. In the middle, you see the picture in optical. These are all galaxies. Each point here is a galaxy. In the center, you see the largest galaxy with a supermassive black hole of about 10 billion solar masses, 10 to the 10 solar masses. This is a huge black hole in the center. On the lower right, you see in red the jets, which you see in radio, because these jets are very fast. They have strong magnetic fields with high energy electrons, and the electron spins around the magnetic fields and emit radiation because they are accelerated in the radio band. And the big picture on the left, this is everything together. So we see the dot, which beside the star here, all are clusters. In the center, you see the largest, all are galaxies. So this is one cluster, many galaxies. Each point is a galaxy. In the center, you see the largest galaxy, and it's jet. So these jets clear the ways. There's a hot gas, the jets go and clear the gas and makes this empty bubble. Someone can answer me if you see my cursor, the arrow. Can you see it?
Yeah.
Okay, good. So we have holes here. So I showed you this. No one will argue that in this case, we have jets that clear this bubble in the hot gas. And this is cluster of galaxy. Here in another example, here I put in white on black, you see the same picture. You see this S shape. You see here on the right, and you see on the left, but. The nice picture that I added now in white is a planetary nebula. The same shape like the cluster of galaxy in X-ray hot gas. We see planet in the planetary nebula in the optical, because planetary nebula, the white, the temperature is 10 to the 4, while in the cluster, the temperature is 5 times 10 to the 7 Kelvin, okay?
And
here's again, yes, please.
What is producing all that X-ray emission? What is heating so much the gas?
This is a good question. When you form the cluster, the gas falls in freely and then pass through a shock. And the velocity is about 500 kilometers per second. So the post-shock temperature is about 50 million degree Kelvin, 5 times 10 to the 7 degree Kelvin. And it stays hot and cools and emit X-ray. The jets keep heating the gas and keep the temperature as 50 or 30 million degree Kelvin. So it emits energy as electron are accelerated near protons, or electron recombines with ions of oxygen and iron and so on, and they emits X-ray, okay?
Okay, thanks.
And you see the same shape. But again, the white picture you see here, it's in optical 10 to the 4. So here is again my cluster. Here is again the white picture I showed you, which it was taken from the ground. The same planetary nebula, if you look with the Hubble Space Telescope, now you have much better resolution and you see all the fine details. The same picture, the white picture on the upper right is the same as the left picture. Just the left is the Hubble Space Telescope, much higher resolution. So I have no, I'm sure jets shape this planetary nebula. Another planetary nebula. So now I come to planetary nebula, which is my main research interest, and we have beautiful picture, which I just look at the picture and see lots of physics. So here you have a picture of one planetary nebula. It's called the necklace. So you have here, because you see all this nice, like a chain, you know, of beads here. And this chain got the name necklace. Okay. And there is a binary star inside with an orbital period of 1 day, more or less, but it wasn't there. Before, it was probably orbital period of a year or several years, but when the star expanded to become giant, asymptotic, giant branch star, it swallowed the companion, and the companion spirals inside in the envelope, and the orbital distance, it became smaller and smaller, only 1 day. But what do we see here? Look, we see jets on the upper left and lower right, we see jets. And if you take picture instead of here, you see the picture, okay, nitrogen 2, which show you low ionization gas, lower temperature and denser clumps mainly. So you see all the clumps in the ring. When you look at H alpha, which is the hydrogen line, you see more gas around, okay? And here, oxygen 3 line, you see again that it is very nice picture. And there is even a better picture that you see here. This is the same planetary nebula. Look, the necklace ring that look like chain, okay, that you have here, jewelry. And you see the jets that really, really go out. And you see, look at the bubble here and here. These bubbles is like in the cluster of galaxies, and cluster of galaxies, where you see the hot gas with the bubble, everybody agrees that these are shaped by jets. So I claim this planetary nebula also was shaped by jets. Okay, here it is again, but now I show you other object. On the right, lower right, you see another planetary nebula, my CN18. And you see its ring, it's kind of one shape like this, another side, and you see it on the side, and there are rings. If you look at supernova 87A, this is an old picture before the exploding material ejecta reached the inner ring, you see 3 rings, one in the center, one above, one below. So here there is one ring in the equatorial plane, like you see in the small one, and in the small ring on the right side of my CN18. And then you see here, you have several rings in the planetary nebula. In 87A, you have only 2 rings. Now, this planetary nebula, MYCN18, was shaped by jets. I will show you in a moment, okay? Now, Super 87A was shaped, and the evolution was influenced by a binary companion. There were other arguments. Here you see the ring of outer ring of supernova 87A, okay? This is supernova, the ejecta you see here in the center, this elongated structure, purple, this is the ejecta from the explosion. This is an old picture, 2004, because now this ejecta already reached the ring. But before it reached the ring, it was hot and it ionizes the ring here. And you see, it looks exactly like the necklace that I showed you before of a planetary nebula. And here are the outer ring of 87A as well. This is only the inner ring that you see here and you see here. The outer ring, you don't see in the picture on the left. Okay, again, this is a ring of the necklace planetary nebula. This is another planetary nebula near the ring. This is Eta Carina. Eta Carina is a very massive binary star. The two stars mass together is something between 150 to 200 solar masses. Very massive binary star. I will show it later again. So look how the ring that was shaped in 87A, similar to a planetary nebula. In the case of supernova 87A that exploded in 1987, in February, we saw the light. I was a young postdoc. In that case, it was a massive star. Now, the ring was ejected from the star. We can calculate it from its velocity and size. It was ejected from the star 20,000 years before the explosion. And the model is that the star expand, swallowed a companion spiral all the way to the center and was destroyed. But while doing it, somehow it shaped the ring 20,000 years before the explosion. Now we already saw the jets in the necklace nebula that I showed you on the right. What about the one on the left? Here is the one on the left. The one on the left here is what you see here on the left. It's the same planetary nebula on the right, but on the right we have a wider field of view. So you see that the nice picture on the left that was taken with the Hubble Space Telescope is only the very inner part of the right picture. But when we look on a wider field, what we see the jets. So this planetary nebula was shaped by jets. So I think that 20,000 years ago, before the explosion of supernova 87A, jet shaped the ring. Of course, remember that supernova 87A in the Magellanic Cloud, so there were 150,000 years until the light reached us, but we speak when the light reached us. Okay, here is another planetary nebula. Okay, you see on the right side the necklace that I showed you before, and here on the left you see a HST image of another planetary nebula. Okay, also you see the ring here. There is a ring which is made of clumps, but you see the elongated structure going from upper left to lower right. So I think this was also shaped by jets. Okay, what is Eta Carina? So on the lower figure, we see the three rings of supernova 87A. Eta Carina is a very massive binary star, as I told you, very eccentric. Every 5.5 years, the two stars come very close to each other, and there are several kinds of activities, disappearing of X-ray, some emission lines that become stronger or weaker, and so on. And this, I claim, also was shaped by jets, okay? So how do you make jets? In order to make jet, I told you, we assume that you need an accretion disk, because in active galactic nuclei where there are supermassive black holes, we see jets when the supermassive black hole accretes mass from an accretion disk. In young stellar objects, we see jets, very narrow, very nice jets, and we see large accretion disks where planets can form. But in addition, the disk gas flows to where the star, and there is accretion. So I assume you need an accretion disk, but to have an accretion disk, you need lots of angular momentum. In young star, this is not a problem. You have huge clouds that contracts to form the star. In active galactic nuclei, it's not a problem. You have gas in the galaxy that falls to where the black hole, and it's fall even a little bit of angular momentum. When it is far away, when it comes in, it spins up. But how do you get it in an evolved star that is small and then expand to be a giant? So I think one of the ways is that if this giant transfer mass to a companion, and because of the orbital motion, this gas has lots of angular momentum, and it is accreted onto the small companion, through an accretion disk. And this disk launches the jets. This is blowing the jets, one jet on each side. Okay, here is again, upper right, the ring, inner ring that was ejected by the star 20,000 years before the explosion. Here is a necklace, a planetary nebula that we know was shaped by jets because of the lower right, we see the jets. And these are Eta Carina and 87A. So now I will show you some simulations. I will come back to some of these objects later. Let me go to another planetary nebula, which I didn't show yet. And let me describe as one simulation that Muhammad Akashi did in 3-dimensional with the code Flash. So what we assumed is that some binary interaction first ejected a spherical shell because of some perturbation. Then the companions start to accrete mass and blow the jet. And so we simulated jets, namely fast collimated gas that is expanding to the shell. So what you see here is density map. Red is high density on the right, and blue is low density, and green in the middle. So you have red, yellow, green. So the highest density is red and yellow and so on. So this is at the early time. On the right side, you see at later time when the jets start to interact with the shell. This is a spherical shell. These are 3-dimensional simulation. And when we continue to later time, the jets break out through the shell and eject lots of material. There are lots of instabilities, lots of instability. We call it column crown. It's like a crown on the head. And this is 3D image of the simulation that I showed you. Previously it was, okay, here what you have is a cut through the center. Okay, the jets are blowing along this axis, up and down. So we have symmetry axis going up and down, equatorial plane going into the screen and out. And when we put, and this is a cut through the center, you see a cut through the center. When you take 3-dimensional view, you see dense material inside in blue, and in the green, you see outer parts. Because of instability, they have fingers going out. And we compare it to this planetary nebula. There's 2 pictures on the left are the same planetary nebula, just different presentation of this planetary nebula. And this is a Hubble Space Telescope image. So we think jets can form many, many kind of shape, and also rings and so on. This is Eta Carina. We also see materials out, and we think maybe this material also was part of the shaping of the jets. Eta Carina had a huge outburst from 1837 to 1857, namely from 100, I mean, it's a long time ago. Almost 200 years ago, from about 180 years ago to about 160 years ago. So this nice shape that you see here, this spinach shape or bipolar nebula that you see, was ejected more or less 170 years ago. Okay, so for launching energetic jet, there is a need for a rapid mass accretion. Can a star companion, like a main sequence, can accrete lots of mass? So we don't know yet, but I think it can. And these people wrote a paper, and they support the claim for rapid accretion from observation. They write, all main sequence companions of planetary nebulae display this envelope inflation. Namely, you have the inner star of a planetary nebula is a star toward the white dwarf. It's a very hot and small star. Its companion is the main sequence. But what they see that the main sequence seems to be inflated, like it accreted mass from the envelope during the common envelope evolution. And I would say that the star accreted mass, the main sequence star accreted mass from the giant. And what it did, it launched jets that shaped the planetary nebula. Eventually, we end up with a compact hot star that ionizes the planetary nebula. It is on its way to become a white dwarf. And it has a main sequence companion that accreted the mass. And actually, the jets came from the main sequence companion, not from the central star of the planetary nebula. They started several years orbital period. Now the orbital periods, as we observe in planetary nebula, the orbital periods typically are between few hours to several days. Questions, please. I'm going and nobody asked me, nobody tell me all my modeling is wrong, nothing. So please ask, give comments, okay? Are you there? At least somebody say yes.
Yeah,
Hi,
yeah.
Noam. Okay,
Yeah,
so
okay.
let me ask you a
everyone is-
question. Let me ask
Yes.
a question while we're here.
Okay.
So how do you get the main sequence star to launch the jet when it's inflated? Or is it launching the jet before it's inflated? At what point?
No. Yeah, it's a good question. The main sequence star is inflated a little bit, not much. You still see a main sequence star, but it's a little bit larger than what you would expect for the same mass. Okay, so instead of, say, if it's star of 0.3, instead of half a solar radius, it's a little bit larger. I don't remember the exact numbers. Okay.
But how does it launch the jet? What's the mechanism for launching the jet?
From the accretion disk. Okay, so you have a giant that transfer mass to a companion, or the companion inside the envelope accretes mass, but because of the orbital motion, the mass that is transferred from the giant to the compact star has angular momentum, like in cataclysmic variables where we see main sequence star transferring mass to a white dwarf. This is an old system that once was a planetary nebula. And we see accretion disk around the white dwarf. Here we have a giant, transfers mass to a main sequence star, but because of the orbital motion, the gas comes with angular momentum. Imagine you are the main sequence star, you see the giant orbiting around you. So with the mass accreting toward you, you have mass coming towards you, you see it orbit around. So it has angular momentum and it forms an accretion disk around the main sequence star. And now the main sequence star has an accretion disk like it had when it was a young star, like this. Our sun had an accretion disk and the planets were formed from this accretion disk, from the dust, the accretion disk and gas in Jupiter and Saturn and so on. But in the very inner part near the sun, this accretion disk actually launched jets. We see it in most young stars that at one time or another, they launch jets by the accretion disk. So the jets come from the accretion disk, not from the main sequence star itself. Okay.
But then you're saying that the accretion disk actually can get hot enough so that it will launch a jet that is fast enough to then afterwards interact with the surrounding medium.
Yeah, the jet is fast enough, but the disk do not need to be hot. In young stellar objects, the disk actually is cold, is forming planets. The main mechanism is that you have the rotational energy of the disk around the star. So you have the orbital energy. And what we think, we don't know exactly, but what thinks that we have a dynamo in the accretion disk, that the dynamo amplifies the magnetic fields. And the magnetic fields have enough energy to transfer the rotational energy to outflow energy along the axis, two sides, two jets. Okay?
Okay, thank you.
This is clear enough, or should, if you have more questions, that's fine. It's a good question. I didn't. Okay.
Hello, could you come back to the slide before this one? So
Here to here.
So you're saying all these systems need to have a companion to form a jet?
Yes, I think that evolved stars, in order to have jets that shape the nebula, need to have a companion because you need a source of angular momentum. You need a source of angular momentum.
You think it's not possible to have for a single progenitor, you have angular momentum in the center, so it forms a jet?
it might be massive stars that do not lose so much mass that the center will rotate fast after it collapses to a neutron star. This is possible. But here we have a giant star that somehow has a bipolar outflow. The bipolar outflow has a velocity of only 10 to 20 to 30 kilometers per second. Usually outflow from stars are about the escape velocity. So if the velocity is 10, 20, or 30 kilometers per second, it means that the star lost the mass when it was a giant, because the outflow velocity from the sun is 600 kilometers per second, the escape velocity from the sun, and the solar wind is 600 kilometers per second. But planetary nebulae and the rings of supernova 87A are only 10, 20, 30 kilometers per second. So the star must have lost them when it was a giant. And when it's a giant, it must be rotating very slowly. There is no source of angular momentum. So yes, I think that in order to launch jets, you must have angular momentum to form an accretion disk, and this must come from binary interaction. And indeed, in most planetary nebulae, we see, when we have good resolution, we see binary in the center. Remember, sometimes because of the common envelope, you have a giant that expands, transfer mass to a companion, and it launches a jet. But after it swallows it, in many cases, the companion spiral inside. This is a common envelope, and collide with the center and disappear. In many other, it ejects the envelope, and you end with two stars, one to become a white dwarf, the central star of the planetary nebula that ionizes the nebula, and the other one is the main sequence star.
Okay, thank you.
Here I have a collection of different kind of objects. Let's go over the object, because I think the comparison is very important, because there's common physics. I don't put here cluster of galaxies that have similar shape, because I concentrate on star. Upper left, MYCN 18, this is a planetary nebula. Another planetary nebula, IC 418. Another planetary nebula or symbiotic star, NGC 6302. All the shape, and HB5, which I showed you before. So the upper four are planetary nebulae. Let's go down to the lower one. The left side is supernova 87A. It's not the explosion inside. There are rings that were ejected 20,000 years before the explosion. What you see here, the 2-1 Kepler supernova remnant, and the other one actually exploding a star, white dwarf that exploded, supernovae 1A. So somehow supernovae 1A, which are white dwarf that explode and leaves nothing, somehow they also have kind of a shape. We call them ears here. I'll show you in a moment. This is a young star, or young star in star-forming region. So young stars also have jet, and look at the nice bipolar shape. Not so symmetric, but still nice. This is Eta Carina, very massive two stars. And we think that the companion star accreted mass here at a very high rate, 1 solar masses per year during the eruption 170 years ago. Now I come to, again, to supernovae 1A, which is the white dwarf that exploded. And you see, we have what we call them ears. Okay, ears. We have ears like ears from this shape. And we see ears on the side here. And I think these were shaped by jet. This is a numerical simulation that a former PhD student, Danitza Brenkok, did almost 10 years ago, 8 years ago. And here you have, again, collection of planetary nebulae. Look at all these planetary nebulae. You have ears here and here. This is a different. Here you have very small ear, the one, okay, the one in the center, here and here. And here you have kind of two jets with the ears here. Another planetary nebulae with small ears here, and another one here. So we have these ears that I think were formed by jet. Actually, it's a very new paper that Muhammad Akashi and I wrote about formation of ears with jets, okay? So maybe the white dwarf, before it exploded, it interacted with a companion somehow, and the companion formed shape, and the explosion was into this nebula. I mean, like 87A that I showed you, the explosion was into these 3 rings that were ejected 20,000 years earlier. Maybe exploding white dwarf in some cases also expelled gas several thousand years before the explosion, and then the explosion was into this gas that had the shape of a planetary nebula that formed the white dwarf. I will not get into it here, okay? Let's talk a little bit about common envelope, okay?
Sorry, Noam.
Yes.
I have a question there.
Please,
so,
very good.
So would this favor more, so the shape of this nebulae, would it favor more the double, oh, I forgot the name, the double compact, so the merger or the mass transfer?
Okay.
Single degenerate or double degenerate? Yes.
Yeah, you caught me. Yeah. It's a very good question. So I say neither this or this. So there are 2 old models for our exploding white dwarf. One is you have 2 white dwarfs that merge together and explode. Another one is if you have regular star, main sequence of giants that transfer mass to a white dwarf, the white dwarf grow in mass until it reaches a Chandrasekhar mass, about 1.4 solar mass, and then it explodes because it contracts and heats up. I have developed a model in between that you have a giant that swallows a white dwarf. The white dwarf spirals inside, collides with the core. So now instead of 2 white dwarfs, you have a core and a white dwarf that merge to give you a very massive white dwarf, which explode only later, say after 10,000 years or 20 or even longer. And during the common envelope, the white dwarf that was spiraling inside the giant through the mass. So the mass went out like the rings of 87A, but now it's not an exploding massive star, it's exploding white dwarf. And in the Kepler supernova, we see gas here that was not part of the supernova, it was expelled. I mean, the star lost this gas thousands of years before the explosion, in the case of Kepler. So we know that some type 1A supernovae, which are not massive, they're low mass white dwarf, came from low mass stars. These are white dwarfs that are exploding by nuclear reaction, not the collapse of a neutron star, not to confuse them. So I think that in some cases, the explosion happened hundreds to several thousands of years, or even 100,000 years after the common envelope. And the gas is still there with a shape like a planetary nebula. Imagine you take the closest planetary nebula that you see here in the picture, okay? Imagine that you take this planetary nebula that we see here, this one, okay? And now you take it and you explode something in its center here. You explode something in the center. You set an explosion here. So the explosion will be, even if it's spherical, it will see this ear that you see here and here. So the explosion will go easy along this direction. And after a long time, you see the explosion almost spherical, but it breaks out more easy along the polar direction, along this direction, that I think was shaped by jets. Else, it might be that the explosion itself is a very fast rotating white dwarf that has jet. Did I answer your question?
Yes, thank you. The only new doubt you created with this is how do you manage for the white dwarf to, I guess it goes into a common envelope and then it goes into the core of the star.
Yes, it merges with the core because it cannot manage to eject the envelope. Yeah.
So, okay, so the core is bound enough that the jets cannot destroy it. Okay.
But it can be also the double degenerative. The white dwarfs end around the core and eject, and after 10,000 years, the 2 white dwarfs merge, and it's double degenerate with the material around it. It can also be the case. But I don't think it's a single degenerate where you have a giant, because giant by itself cannot lose so much mass. And we don't see in Kepler supernova, we don't see any giant.
Okay,
which should have survived after the explosion. But I don't want to get to type 1A supernova, it's completely, okay?
Thanks.
Good. So let's go to common envelope. So what do we have? we have, this is a simulation that we have an AGB star initially, and a companion gets in and orbits around. And the model is that companions get in. When it's get in, it releases lots of angular energy, lots of gravitational energy because it's spiral in, and angular momentum. So the envelope spin and it ejects the envelope. But most simulations fail to eject the envelope. Most of the envelope stay bound. So you inflate an envelope, it becomes larger, but you do not eject it. So I think in some cases, a companion, not white dwarf, but a main sequence or a neutron star can accrete mass, launch jets that explode the envelope. Okay, so let me, yes. So what is the model? The model is like this. We have a giant and we have one companion, it's a secondary. I show it twice, so it's not two companions, one companion. So we have what you see in black is the core of a giant star. What you see in red is the huge envelope of a giant star. It can be red giant branch star or asymptotic giant branch star or super red giant if it's very massive. And then we have a companion. Mass from the red giant is flowing toward the companion. I didn't show it, but there is a stream of gas from the envelope, okay, stream of gas from the envelope that goes toward the companion. I mean, there is mass that going here toward the companion. Now, because of angular momentum, the rotating, the angular momentum axis is up, down in the figure. So we form an accretion disk. What you see here in yellow, this line that I put in red now, it's an accretion disk. And the accretion disk rotate around the main sequence star or neutron star, and two jets are launched by the accretion disk. It's the accretion disk that gives the jet. The energy comes from the accretion because it's from the star and liberates gravitational energy, and the jets are formed by magnetic activity of the accretion disk, okay? And these jets are very energetic, and when the star gets inside, it can get inside into the star, and when it gets inside to the star, it starts to orbit inside and launch the jets, and the jets can remove the envelope, okay? So there are several common outcomes. Can be more merger at the end of the common envelope. I don't want to get to all what is written here. I will mention the grazing envelope evolution. Imagine that the companion now gets inside. So in the classical common envelope, the companions get into the envelope. But now if it launches jets, the jets can remove the envelope. So the companions stay all the time on the edge of the envelope because it removes the mass. It grazes the envelope. This is grazing coming on the edge. So I call it the grazing envelope evolution, and I developed it in about 6 years ago.
Noam?
Yes.
So let me just tell you, Enrique actually has another name for your grazing envelope evolution. He calls it the potato peeler every time that he talks about it.
Okay.
But so what do you think is more common? That the jet peels the envelope, or that the jet is not energetic enough and is able to, so that the compact object enters the common envelope and then energizes the interior?
Yeah. I think it's a good question. I think in massive, if the companion is massive enough, it will be grazing. If not, I think. So it depends on the mass. I think in most cases it enters the envelope.
Okay.
Because its mass, it's not high enough. So I have some movie here. I don't know if it works, but let me try. Okay, maybe I think stop share and then share something else. Just a minute. I need to see if it will work. If not, just a minute. I should have prepared it. Okay, it goes here. Should go somewhere. Just a minute. Sorry, I should have. Okay. Just a minute. Now I'll share it. Yeah. Do you see the movie now?
Yes.
Yeah.
Okay. So what you see here This is a movie that Sagiv Shiber, my former PhD, who is collaborating with people here, made. So what you have here is actually, we don't simulate the accretion, we just set kind of a star inside an envelope and let the jets go out. So this movie repeats itself. So when it starts from the beginning, you will see kind of two jets going out and cleaning the envelope. We will watch the orbital plane. So one jet coming toward us and one goes into the screen. Okay, and then we will see it cleaning the region around it. So here's what you see. This is exactly the neutron star in the orbital, not neutron star, main sequence star, excuse me, with the jet. And you don't see the jet, but the jet deposit energy to the envelope and throw the material out. And this is a grazing envelope. The jets continue to be, the companion is on the surface. Here you see a 3D picture, which at the beginning there is a mess, it's a limitation of the numerical simulation, but at the end you will see the two jets in blue. Blue are two jets, but because it's moving, the jet stays around, and in red you see the envelope being ejected. Not all the envelope, I show you only the outer edge. This is very difficult to see in 3 dimensions. Here you see again the companion with the jets going around. Here you see the temperature. Red is very high temperature because the jets are shocked. And this is exactly this jets in the envelope. So this is the movie, yes, I wanted to show you.
A
Okay?
question. How
Yeah.
much mass is accreted with respect to mass, which is
We
ejected?
don't simulate the accreting. We don't have the ability. We assume that the accretion rate is a small fraction, like 10%, below 50%, typically 10% or even 1% of the Boindy whole little tall accretion rate.
Okay, thank you.
So we did not do all, okay?
Sorry, a question regarding that simulation.
Yeah, please.
So if I understood correctly, the companion that is raising the surface and is launching the jet, that jet is being put by hand in the simulation.
Yes,
So
yes. We don't have yet, because if we don't do it, we need to resolve. Even a main sequence companion is only 1 solar radius. So we need to have resolution of at least 0.1 solar radius, but size in 100. So we don't have the computer power to do it. Okay?
Sure. Thank you. Yep.
So I have more movies, but let's go on. Core collapse supernovae. Core collapse supernovae, this is a different story, but I just want to give you a broad vision how angular momentum is very important in stellar evolution, not only in planetary nebulae and non-exploding star, but also on massive star. So, convinced by the shaping of planetary nebulae by jets, that I showed you many pictures so you get what I'm aiming at. In the last 5 years, we compare them to supernovae remnants, namely a star that exploded, massive star that exploded that we observe now, hundreds to thousands of years after the explosion. So let's look at a picture. Here's in planetary nebulae and supernova remnant of massive star. So I show you ears, okay, ears of planetary nebulae. So these are planetary nebulae on the upper row. But now I move to supernova remnants of massive star. Adana Gwichner, who just finished her master's degree with me, did this work while still being an undergraduate. She marked all the ears in supernova remnants of massive stars. And you see the ears, one here, one here. Here you see an ear, here you see an ear. And I see similarity in the shape. Here in supernova remnants is typically not optical image, but X-ray or radio, but it doesn't matter. We're not going to what. Here is an H-alpha image as an example. In other cases, on the left side, it's X-ray and so on, but it doesn't matter. I look on the shape and you see ears in supernova remnants, and I think all these were shaped by jets. And I think these jets also exploded the star. So let's see more examples. Look at the planetary nebulae. You see the upper left one, you see the S shape. You see S shape also in the lower left in W44. You see also S shape, okay, of the, here you see an S shape, here also. Many similarities. These are different planetary nebulae. Here you see Cassiopeia A, the famous one with its jets. There's something small on the left, okay? And this is a different image. You know, you have radio, you have X-ray, and so on, and you might see jets as well. Here you see another supernova remnant. See the bubble here, and there is something on the right side as well, smaller. And there is a neutron star inside. Here is another example, okay? And Aldana did the calculation, Aldana Greichner, and she found that the typical energy in these years is about 1 to 10% of the total explosion energy. We think that there were several, not only one pair of jets, several pair of jets exploded the star. And what we see with the ears is only the last jets. So it has 1 to 10% of the energy. Okay?
May I ask something there again? Sorry, Noam.
Please, please. No, it's good. It's good. Questions are good.
So, so you have the remnant. In some cases, you mentioned that you can actually find the neutron star. Can you find as well the companion that induced the angular momentum?
No. So this is my point, that in exploding massive star, I don't think we need companions in many cases, because I think because you take a core of about 2,000, 3,000 kilometers, the iron core at the end, it collapses to a neutron star of only 30 kilometers, and then it shrinks to 12 kilometers. So you have, I mean, from 3,000 to 30, you have factor of 100 reduced in the radius, okay? And I think if you have stochastic angular momentum, very low angular momentum, but at 3,000 kilometers, you have it as in contracting clouds that form young stars. So a little bit of stochastic angular momentum in contracts give you stochastic high enough angular momentum to form an accretion disk that launches jets for short times, because the total angular momentum of the core is almost zero. But because of convection and disturbances and so on, you have a random, chaotic angular momentum. The jets go like this, then in other directions and so on. Okay? I call it jittering jets. But the point here, I don't want to get to this mechanism, it's a talk by itself. The point is, just by looking at the shape and calculate the energy of the jets, you get the picture that the energy of the jets is not negligible. It's 1 to 10% of the energy of the explosion. And it really, this jet really left a mark on the supernova remnants. Okay?
Okay, thanks.
The ears, in principle, the ears remind us the ears of planetary nebulae that I keep all the time on the upper row, that you remember the connection, because in planetary nebulae, we know there are jets. In some cases, we see the jets. Here, we could not see the jets. They were active in the explosion, and this is it.
Noam,
yes.
Just did I understand correctly that you said that the angular momentum of the collapsing core is negligible? I always thought that the collapsing core has a huge angular momentum.
Well, the total average angular momentum is not enough to form an accretion disk, okay? This is, I mean, negligible. But because of convection motion in the core before the collapse, you have stochastic angular momentum, that the neutron star accrete material over about 1 to 2 or even 10 seconds. During these few seconds, you accrete different parcels of gas. Once for about 10 milliseconds, the angular momentum can be in one direction, then for another 10 milliseconds in another direction, and these stochastic direction add to zero angular momentum.
I understand that. I understand that that's what, okay. But why, I mean, the star is rotating. And so
yes, but
as the core is collapsing.
The core, even if the core rotates, is not fast enough to form an accretion disk. It contracts by a factor of 100, but the average angular momentum of the core by all simulation is too low to form an accretion disk.
Okay.
So I have stochastic angular, I think stochastic, it's not the popular model. The popular model is that you explode by neutrinos. So this is why I don't want to get into it.
Okay, thank you.
But I think at least in some cases we do see the mark of jet, and the axis is more or less along the axis also of the neutron star because of the pulsar, because I think the same angular momentum that gave rise to the last jets also gave rise to the angular momentum of the neutron star at the center. Okay, let me show you some other shape and I will end with that. Okay, I need to add. So what I show you, just to close the talk, the one inside the green box is a supernova remnant of massive star. You see kind of elongated shape with a hole inside. And there are some other planetary nebulae with hole inside, like here, you see this. Look here in PN-NGC 40 in the middle right, you see kind of a hole in the center, and in other cases as well. You see kind of a hole in the center, and I think this is another similarity between planetary nebulae that we know were shaped by jets and supernova remnant. Here, the upper four images are the same supernova. The general shape of the supernova is kind of look like bar like this, okay? The upper left. But when you look on the iron, calcium, and argon, you see kind of an H shape. And here on the lower, you see a planetary nebula also with an H shape. And this is a kind of an analyzing this shape, okay? So there are other similarities, like you see here, planetary nebulae with H shape, and similar to the H shape of the argon and iron that are inside of the supernova, okay? And we can have several, and we simulated it again, jets that run into a shell in planetary nebulae, and we form different shapes. You see all the instabilities here. These are all shapes that we formed, Mohammad Akashi, by simulating a jet. And you see it on the left side, just simulation. And I would like to end really with a common envelope jet supernova mechanism. This is a mechanism where a neutron star, not a main sequence star, get into the envelope. The neutron star can accrete mass at a very high rate because of cooling by neutrino. Eddington limit doesn't apply. Can accrete at one solar mass per second. A neutrino takes most of the energy, but not all of it. Part of the energy can go into jets. Only 1%, no more of the accretion energy. And when the stars, the neutron star, spirals inside the envelope, it can release huge amount of energy. And there are people in your institute, and I listed them here, who do very nice simulation of this. And I'll show you one scenario is that you have two main sequence stars that starts, one evolved to a red supergiant, explodes as a supernova, forms a neutron star. When the other main sequence expands to a red supergiant, it swallows the neutron star, and the neutron star spirals inside. And then the neutron star, if you go to the left, can launch jet, or it can eject the envelope and explode to form two neutron stars. And this is from the work of Aldana Gwichner, that you have neutron star launching jet inside the envelope. And you can simulate it, but it's very complicated. But the people here, okay, and I see here Diego and Enrique and Fabio did actually beautiful simulation of this to determine the accretion rate, something we don't have yet the resolution to do. A very nice simulation that you see jet, but you can ask them, you don't need me for that. And here I show you very, very new three-dimensional numerical simulation. We didn't publish it yet, that I do with Shlomi Hillel and Ron Schreier and Sagiv Shiber. Here you see, you can see there is I'll mark it with a black. You see here the neutron star, I put at the arrow here. You see here a neutron star, okay? So, and the neutron star is rotating inside, and we don't have the resolution to do the accretion. We only launch the jets, and a little bit later, the neutron star started here, okay? And it rotated around like this. And after the orbital period is about 4 years, and after 3.3 years, you see it here, and you see the jets. We only deposit energy of jet. There is no gravity of the neutron star. don't have the resolution to show it on the one hand. The other hand, we want to see what jet is doing. And when we continue, you see the two holes that the jets come out and do bubbles and expel gas out. So we see that the jets inside the envelope can expel the gas, and this is the resolution. Takes lots of computer time, but this is the simulation, okay? Okay, another group of objects that might be shaped by jet are merging stars. When two stars merge, one of them can accrete mass or be distracted, form an accretion disk, and launch jet. This is very interesting object. I will go very fast over it. It's called CK-Wool or Nova 1670 because it exploded 350 years ago. And the likely explanation is not a nova, which is the eruption of a nuclear outburst on the surface of a white dwarf, but rather merging, two stars that merge together. And this is from Kaminski and Steffen and other. And you see here the two lobes that I think were shaped by jets. Again, by jets, okay? So I took a little bit all the time, 1 hour and 15 minutes. So I put my summary again, but I already showed you the summary, the same summary at the beginning. And I will be happy to take more questions and to have a discussion. And thank you very much.
Thank you very much, Noam. Very, very nice talk. Especially slide 54 was wonderful.
Amazing talk. Thank you very much.
So
Emilio,
no
please.
question.
Emilio has one.
Okay. Yes. Thank you very much for such a beautiful talk. It was very interesting. My question is, would you consider other possible mechanisms, or have you considered other mechanisms for the ejection? I mean that you don't necessarily need, I can see how having jets work, but I also think you might have slower winds or just outflow in the form of a bipolar outflow that can maybe give you these geometrical features that you have shown that appear consistently in many different systems. So my question is, does it necessarily have to be a jet or just some kind of loose outflow, bipolar outflow, the one behind these geometries?
Okay, this is a very good question because in the past, but let me look, okay, I need to find a good image of a planetary nebula and explain you why I think these are jets, but I don't know if specifically here I have one. Okay, I have this one, okay. In the past, I mean, 30 years ago, people working different mechanisms say, okay, we have a red giant, it's rotating slowly and it expels mass in the equatorial plane. Now comes the fast wind, and the fast wind cannot break in the equatorial plane because there is a ring there, so it breaks in the polar direction. And people did simulations, even I did. What is the problem with this model? This model works for over a long time. So you have the equatorial ring, and now you have fast wind. So you have only one shape. But look at this. Let me use my pen again. Look at this planetary nebulae that I show you on the left, which is with the Hubble Space Telescope. You see this S shape here. You have S shape. You see my yellow marker? See, the dense part here is S shape. And we think this is precessing jets. And in order to have precessing, you need an accretion disk of precess. You need to have some precession. And in order to have precession, you cannot have this mechanism, which is called general interacting wind model. And this is why I think we have jet. In many cases, and this is one example, okay? We have other cases that we have other cases where we do see precessing jet. Even here you can see it, but this is weak. I look for other cases because I didn't prepare many images with precession because there are some beautiful examples that you cannot explain other than precessing jets. Okay. in some of these cases, you might see precessing jets, not here. So I didn't prepare these, but you really see precession. And in one case, that it was Nature or Science, they really see real precession. You see nice picture, I didn't prepare it here, and you see binary inside. So both we see binary and we see precession. It must be jets, it cannot be other mechanism. Okay? Now
No,
also—
sure, thank you. Yeah, so I guess what I meant is that for sure jets work in and can work in many cases. My question was more like, could it be that something is lower, but that has the right geometry, so just a bipolar outflow that is not as powerful as a true jet? Can it be maybe behind some features that are not so prominent as the ears that you are showing in this slide? So this is evidence that something was with a bipolar structure, but at least wasn't as powerful as the ones that you were showing before, no?
Well, I don't know what you mean, but there are other effects. Like if you have a common envelope, the common envelope ejects dense material in the equatorial plane. So we have other effects. If the star gets inside, we have rotation, it can throw material. So I don't claim jets are the only shaping mechanism. If you have a binary, you have common envelope, it can spin up the star, then there might be more mass in the equatorial plane. You can have magnetic activity which eject faster material on the polar direction, like in the sun. In the sun, there are no jet, no binary companion, but a little bit rotation. So you are right. There are other effects. I don't claim there are no other effects. We know there are. The common envelope eject in the equatorial plane. We see the ring in supernova 87A. This was a common envelope that ejected the ring. We see magnetic activity. We measure magnetic field from AGB star giant. So we know magnetic field plays a role. But I think the main role is, in many cases, are jet, but they are not the only one. I hope I answered part of the question.
Yeah, thank you very much.
Felipe?
Hi again. I would like to ask two questions. The first one is that, had you used magnetic field in your simulations?
Very good. No, I think to use magnetic field in these numerical simulations, I mean, you need a real strong computer. So I think it's very hard. But I did use in analytical estimates. In many analytical estimates, we do put magnetic fields and people observe magnetic fields. So there are magnetic fields, and I think they also do some shaping, but not as prominent and not so extreme as jets.
Okay, and the another one is how challenging would be to in the simulation you did the jet, but you didn't consider the accretion disk. How challenging would be to consider the accretion disk as a source of the jet?
Accretion disk and jet together will be very complicated. The people here, Diego and Enrique and Fabio, they do nice simulations. They include it, but I think they are limited. They can say more by the time of the resolution. They do resolution inside for a short time. If we do the resolution for several, we want to resolve several orbits and the region around the star, it will be very hard to include the accretion. The accretion process is very complicated, very complicated. And to have the accretion disk, then it's even more complicated. To have jet from the accretion disk is impossible, because even people who do only accretion disk around stars cannot get jets. In order to get jet from accretion disk, and they have no accretion, nothing, that you put the disk, they need to arrange the magnetic field. They cannot let the jet evolve, develop its own magnetic field and have jets. Nobody got to this stage. Only people who have put accretion disk, put magnetic field, then they get some jets. So it's very complicated.
Okay, thank you.
Diego?
Okay, so yeah, we are unfortunately limited in small time and small domain, but we do manage to see the accretion rate. But my question is actually not concerned with this. What I don't understand is, how does the jet help in the, like in supernova 1987 and all these planetary nebula, create the necklace in the equatorial plane?
Oh, I didn't prepare the simulation. Muhammad Akashi did the simulations of that you launch. This is. If you give me 1 minute, I can look for it, or you can stay later. He did simulation. What you have, you inflate bubbles, and the bubble compressed because the bubble. Let me draw a picture here. This is okay. So if I draw, the jets go out. One jet here. I use a blue empty area, and it inflates a bubble here and here, and these bubbles expand to the side. But both bubbles expand toward the equatorial plane. So you compress the material here, around here in a disk, and this becomes a stable and you form the necklace.
Okay.
But it can also be maybe if the star rotates and you don't need jets. I don't claim jets are the only effect, but we managed to do it in one of the simulations. Okay. It's not perfect, but we can do something similar. I didn't prepare it here because the talk is already long, so.
More questions?
Yeah, I have a final question here. I'm Gloria Königsberger. There are a couple of Wolf-Rayet stars that have a bubble around them. And these bubbles have what I have always thought are breakouts. And they remind me of what you call ears in the structures that you showed. Both of these Wolf-Rayet stars, we claimed many years ago that were binaries with a collapsed companion, but the X-rays coming from them are not sufficient to prove that there is a neutron star there. In more recent years now, we're leaning more to the possibility that it's a main sequence-like type star. And so I'm wondering, what would we need to do to show that these main sequence stars, if they exist as companions to the Wolf-Rayet star, are driving such a jet as you propose?
Do you think they're driving the jets now or in the past? So,
well, the bubble is large. It must be like 10 to the 4 years old.
Oh, so it might have been in the past. So I don't know how you go now. But if you find a main sequence and you see it's not on the, if you know its mass, it's not on the right position in the H-star diagram, you might claim it's accreted mass. Or if you see leftover of the jet. I'm very interested now in these two nebulae. If you can send me, or I send you an email and you send me them, I'm very, very much interested to look at them.
At least you can add them to your collection of ears.
Yeah. Yeah, definitely.
Okay, yeah, I will be gladly send you the names.
Okay, good.
Thank you.
Yeah, it will be interesting.
More questions? Okay, if there are no more questions, please turn on your camera just to say goodbye to the speaker. Thank you very much, Noam.
Thank you.
Thank you. I enjoyed it a lot. This was a good experience. Thank you very much.
Thank you.
Very nice talk. Thank you. Noam.
Noah, I would like to personally thank you for the corrections on my paper on arXiv you sent a few weeks ago. So thank you.
With the time scale.
Yeah, and the
size was 1.6, 10 to the 16 or 17.
Yeah.
Okay.
So, thank you.
No, you see, I take seriously paper on the arXiv. Good.
Okay, see you next week. Bye.
Bye-bye. Bye.
Bye.
Thank you very much.
Bye.
Bye.